In this video, I'm going to show how to use AgenaRisk's table learning function, which you can access with that icon there, to learn the probability tables for a model with predefined structure like this, where there's a limited data set and where we also want to use knowledge. The idea of this model is that a person's marital status and sex influences whether they work full-time or part-time, and their marital status and work status influences whether they need to be on benefits or not. Now, as you can see, in this model, we've only got the structure. We've got nothing other than default probability values here, so this model doesn't incorporate any knowledge or any data. The data I have in this case is incredibly limited. I've got just 10 records in there. The headings here correspond to the nodes in the model. We need that in order to automatically learn from a spreadsheet. But notice things like there's only one female single, and that person happens to be full-time. So there are no female singles working part-time in the data set, even though they obviously exist in real life. So that already constrains severely what's going to be learned here. But let's try it out, just learn without any knowledge in this case. So I'm going to select that data set, this one. It's recognised only 10 cases in there and 4 variables. I'll accept that. I'm not going to incorporate any expert judgment. I'm just going to run the model. It's learnt some stuff, but I'll show you what it hasn't learnt and what it has learnt. So in this work here, notice this. Female single, because there was only one person, they were full-time, it's assumed that the probability that a female single can be a part-time worker is 0. Similarly with male singles, I think there were 2 or 3 of those, but they were all full-time. So again, it didn't learn that there was actually a non-zero probability that a male single could also be part-time. And also, notice things like this one here, part-time single. There was no data at all for that. It's simply retaining the original default values. It hasn't learned anything, so it just assumes that they're 50-50, even though it's almost certainly not the case. So it's extremely limited as to what we can learn from the data only. So instead, we might start with a model which has encoded our own priors. So based on knowledge and maybe some other data, we believe that male singles are more likely to be full-time than part-time. Male marrieds are very likely to be working full-time, as are female singles. And we've got some similar knowledge encapsulated here. So for example, part-time people are more likely than full-time people to be on benefits, which is a perfectly reasonable thing to assume, of course. So how can I use that knowledge but combine it with the data? Well, we're going to do the same as before. We're going to select that same data file. But this time I'm going to incorporate expert judgment. And the way we do this is to specify how much weight we want to give to the knowledge compared to that new data set. If I say that I want an 80% ratio of knowledge to data, then it's saying that's the equivalent of having 40 rows which are based on the knowledge compared to 10 rows of data. So that's, now I could set each of these individually as well. So sometimes we might be very confident about one particular probability table from expert knowledge and less so for others. So I can set each of those separately. But I'm just going to by default assume they've all got the same 80-20 knowledge to data weighting. So I select that. I'm now going to run the model. The M symbol here means that it's a mixture of data and knowledge. And now we can see what's going on over here. So for that female single status, it's now showing there is a non-zero 16% probability of part-time because I had a non-zero probability in there in the knowledge. For this one, for the part-time singles, it's no longer 50-50 that they're on benefits. It's significantly less than 50% chance to be on benefits if they're single. So it's learnt from a combination of knowledge and data. So here's an even worse data set. It's like the one we had before, but it's got some missing values in there. Can it handle those? Well, it can. And again, we're going to use the combination of expert knowledge with that data as partial as it is. So in this case, the data I'm loading is this one with missing values. Just saying that the normal default for missing values is NA, but it's recognised there are spaces, so it's asked if it wants to treat those as missing values. So I'll say yes. And so you can see it knows that there's missing values. And in this case, when I run the model, it's going to apply an algorithm called EM learning, that stands for expectation maximization learning, where it's learning the missing values by running the Bayesian network and finding the most likely state of the missing value. Again, I'm going to incorporate expert knowledge. This time, I'll say 75% knowledge to data. Run. And there's the learnt model. We can compare that one with the one that was learnt without the missing data. They're not massively different. So you can see that it can quite comfortably handle these missing values. Obviously, the more missing values, the harder it is to do accurate learning, especially, of course, if you've got a lot of missing values in a very large data set, because it has to do a lot of processing then.